Welcome to this coding problem walkthrough. Today, we'll explore problem number 302, smallest rectangle enclosing black pixels. This is a fascinating problem that challenges your understanding of 2D matrices and efficient search algorithms. Let's dive in and solve it together. In this problem, we are working with a binary matrix called image. Each cell in the matrix contains either a 0, representing a white pixel, or a 1, representing a black pixel. Along with this matrix, we are given the coordinates x, y of one specific black pixel. The goal is to determine the area of the smallest rectangle that completely encloses all black pixels in the matrix. For the input, the matrix dimensions m and n can range from 1 to 2000, and the coordinates x, y are guaranteed to point to a valid black pixel. The output will be a single integer, which represents the area of this enclosing rectangle. Let's consider our first example. The input matrix contains 3 rows and 4 columns. The black pixels are located at specific positions 0, 2, 1, 1, 1, 2, and 2, 1. The given coordinates x, y point to the black pixel at 0, 2. To find the smallest rectangle enclosing all the black pixels, we calculate its boundaries. The top left corner of the rectangle is at 0, 1, and the bottom right corner is at 2, 2. To determine the width of this rectangle, we subtract the column indices 2 and 1 and add 1. This gives us a width of 3. Next, we compute the height of the rectangle. The top pixel is at row 0, and the bottom pixel is at row 2. Subtracting these row indices and adding 1 gives us a height of 2. The area of the rectangle is then calculated as the product of its width and height, which is 3 multiplied by 2, resulting in an area of 6. This means the smallest rectangle enclosing all the black pixels has an area of 6. In the second example, we have a much simpler case where the matrix contains only one pixel, which is black. In this case, the given coordinates x, y point to the single black pixel at 0, 0. Since there is only one pixel, the smallest rectangle enclosing all black pixels is the pixel itself. The width and height of this rectangle are both 1, so the area is simply 1 multiplied by 1, which equals 1. This example demonstrates that the solution must handle the smallest possible input size correctly. Now let's move to another example where the black pixel is located at the center of a larger matrix. Here, the input matrix has 3 rows and 3 columns. The only black pixel is at position 1, 1, as given by the coordinates x, y. Similar to the previous example, the smallest rectangle that encloses this single pixel is the pixel itself. The width and height of the rectangle are both 1, so the area is again 1. This problem also has a few constraints and edge cases to consider. For instance, the matrix can be as large as 2000 by 2000, so any solution must be efficient. Additionally, we need to handle cases like single pixel matrices or sparse black pixels where the rectangle spans a wide area. Keeping these considerations in mind will ensure our solution works for all valid inputs. To solve this problem, we started by considering a brute force approach. The intuition here is straightforward. We traverse the entire matrix to locate all black pixels. By tracking the minimum and maximum row and column indices containing these black pixels, we can calculate the area of the smallest rectangle that encloses them. The formula for this area is derived from the difference between the maximum and minimum indices in both dimensions. While this method requires no extra storage and is simple to implement, it is computationally expensive for large matrices, as it unnecessarily processes every cell, even when most of the matrix is white. This inefficiency makes it impractical for sparse datasets. To address these limitations, we explored an optimized approach using binary search, leveraging the given black pixel's location to minimize the search space. The key idea here is to focus only on the rows and columns containing black pixels, rather than scanning the entire grid. This method is significantly more efficient, especially for sparse matrices, as it reduces the processing to just the relevant areas of the grid. The optimized binary search approach works by narrowing down the search space to the smallest rectangle enclosing all black pixels. First, we use binary search on the rows to find the boundaries for the top and bottom of the rectangle. Specifically, we locate the first row containing a black pixel, which gives us the top boundary, and the last row with a black pixel for the bottom boundary. Similarly, we apply binary search on the columns to determine the left and right boundaries of the rectangle by finding the first and last columns containing black pixels. Once these boundaries are identified, we can compute the area of the rectangle using the same formula as before. The beauty of this approach lies in its efficiency. By focusing only on rows and columns with black pixels, and leveraging the logarithmic efficiency of binary search, we drastically reduce the number of cells processed. The time complexity for this method is O(m log n plus n log m, which is a significant improvement over the brute force approach. Additionally, it uses constant space, making it highly scalable for large matrices. This efficiency is particularly beneficial when the black pixels are sparse and spread out. Another strategy we explored involves treating the matrix as a graph and using a flood fill algorithm like DFS or BFS to locate all connected black pixels. Starting from the given black pixel, we traverse through all adjacent black pixels, continuously updating the boundaries of the rectangle as we go. This ensures that we capture the smallest rectangle enclosing all connected black pixels. The time complexity of this approach is proportional to the number of black pixels, denoted as OK, since each black pixel is visited exactly once. However, it requires additional memory to maintain the recursion stack in DFS or the queue in BFS, leading to a space complexity of OK. While this method is efficient for matrices where black pixels are sparsely distributed and connected, it can be less intuitive to implement compared to binary search. Additionally, for scenarios where black pixels are spread out and disconnected, this approach does not scale as well. Despite these trade-offs, the flood fill method remains a viable option, particularly for problems where connectivity plays a crucial role. After evaluating the different strategies, we chose the optimized binary search approach as the most suitable solution for this problem. The key advantage lies in its ability to independently determine the boundaries for rows and columns, significantly reducing the search space and ensuring efficiency. By leveraging the guaranteed presence of at least one black pixel and its location, this approach avoids unnecessary computations, making it ideal for large matrices with sparse black pixels. While the brute force method is straightforward, its inefficiency for large grids disqualifies it for practical use. On the other hand, the DFS/BFS approach, though efficient for connected black pixels, is more complex to implement and requires additional memory for recursion or queue storage. Ultimately, binary search strikes the right balance between efficiency and simplicity of implementation. It is particularly well suited for scenarios involving structured or sparse black pixels, whereas DFS/BFS might be more appropriate for densely clustered and connected black pixels. By choosing binary search, we achieve a scalable and effective solution to this problem. The problem requires us to find the smallest rectangle that encloses all the black pixels in a given binary matrix. Each cell in the matrix is either 0 or 1, where 1 represents a black pixel. The output should be the area of this rectangle. To solve this, we start by defining 4 variables, min_o, max_o, min_call, and max_call, which will track the boundaries of the rectangle. Initially, we set min_o to the total number of rows m, and max_o to -1. Similarly, min_call is set to the total number of columns n, and max_call to -1. These extreme values ensure that as we find black pixels, the boundaries will adjust correctly. Next, we traverse the entire matrix using a nested loop. For each cell, if the value is 1, we update the boundary variables. For rows, we adjust min_o to be the smaller of its current value in the row index of the black pixel, while max_o is updated to be the larger of its current value in the row index. This ensures we capture the smallest and largest rows containing black pixels. Similarly, for columns, we update min_call to be the smaller of its current value in the column index of the black pixel, and max_call to be the larger of its current value in the column index. Once we finish traversing the matrix, we will have the exact boundaries of the rectangle enclosing all black pixels. Using these boundaries, we can calculate the area of the rectangle with the formula max_o min_o plus 1 asterisk max_call min_call plus 1. This formula accounts for the fact that the dimensions of the rectangle include all rows and columns from the minimum to the maximum indices, inclusive. Lastly, the computed area is returned as the result. Key insights here include the efficiency of boundary tracking, as it allows us to calculate the rectangle's dimensions in a single pass without extra storage. The algorithm's single traversal of the matrix ensures that the time complexity is optimal at O(m*n). Now, let's consider some important edge cases. First, if the matrix contains no black pixels, all boundary variables will remain at their initialized values, and the computed area will correctly be 0. Another case is if there is only one black pixel in the matrix. In this scenario, the rectangle will have a height and width of 1, resulting in an area of 1. For data structures, the algorithm relies only on 4 integer variables to track boundaries, making it highly memory efficient. Instead of storing additional information or indices, we use the input matrix directly during traversal. This keeps the space complexity at O(1), excluding the input. For time complexity, the algorithm processes each element of the matrix exactly once, ensuring a linear pass through all mxn elements. This makes it efficient, even for larger matrices. To summarize, the time complexity of the algorithm is O(m*n), as we visit each cell of the matrix exactly once during traversal. The space complexity is O(1), because we only use a constant amount of space for the boundary variables, regardless of the matrix size. To better understand how this algorithm works, let's walk through a concrete example. Consider a binary matrix with 3 rows and 4 columns, where some cells contain black pixels. Initially, the boundary variables are set to their extreme values: min_row equals 3, max_row equals -1, min_col equals 4, and max_col equals -1. These values will change as we encounter black pixels during the matrix traversal. During the traversal, when we encounter the first black pixel at cell 0, 2, we update the boundaries to min_row equals 0, max_row equals 0, min_col equals 2, and max_col equals 2. Then, at cell 1, 1, we adjust the boundaries to include this pixel, resulting in min_row equals 0, max_row equals 1, min_col equals 1, and max_col equals 2. As we continue, cell 1, 2 does not change the boundaries, but cell 2, 2 updates max_row to 2. With the traversal complete, we calculate the dimensions of the rectangle as max_row min_row plus 1 equals 3 rows and max_col min_col plus 1 equals 2 columns. Multiplying these gives an area of 3*2 equals 6. Finally, the result, 6, is returned. Here, we begin by defining a Python class solution with a method minArea to calculate the smallest rectangle enclosing black pixels in a binary image. The method takes 3 arguments: the image, which is a 2D list of characters, and the coordinates x and y, representing the location of one black pixel. To efficiently determine the boundaries of the rectangle, we use a helper function binary_search. This function performs a binary search on either rows or columns, depending on the input, to find the edges of the rectangle. The parameters include low and high for the search range, check, which is a function to verify if a row or column contains black pixels, and find_min, a boolean that determines whether we're searching for the minimum or maximum boundary. The binary search adjusts the range based on the result of the check function and eventually returns the boundary index. Next, we define 2 utility functions: column_has_black checks if a given column contains any black pixel, iterating through all rows in that column, while row_has_black does the same for rows, iterating through all columns. These functions are used as the check parameter for the binary search process. With these components, we're set up to identify the boundaries of the rectangle. Now, we use the binary_search function to determine the 4 boundaries of the rectangle containing all black pixels. First, the top boundary is found by searching for the first row containing a black pixel, using the range from 0 to x and setting find_min to true. Similarly, the bottom boundary is determined by searching from x plus 1 to the total number of rows, but this time with find_min set to false to find the maximum extent. For the columns, the left boundary is identified by searching from 0 to y with find_min is true, and the right boundary is found by searching from y plus 1 to the total number of columns with find_min is false. Once we have the boundaries, the area of the smallest rectangle is calculated as the product of its height, bottom, top, and width, right, left. Finally, the method returns this area as the result, completing the implementation of the algorithm. Here, we have the Java implementation for finding the smallest rectangle that encloses all black pixels in a binary image. The main method, minArea, takes in the image as a 2D character array, along with the coordinates of one black pixel, x and y. To determine the boundaries of the rectangle, we use binary search. First, the top boundary is found by searching for the uppermost row that contains a black pixel. Similarly, the bottom boundary is located by searching for the lowermost row with a black pixel. For the horizontal dimensions, the left boundary is identified by searching for the leftmost column with a black pixel, and the right boundary is found by locating the rightmost column. Once these boundaries are identified, the area of the rectangle is calculated as the product of the width and height, which is determined by the differences between the boundaries. The binary search method is used for this purpose, and it relies on a predicate function to test whether a given row or column contains black pixels. The binary search method is designed to find the boundaries of the rectangle efficiently. It takes in the range to search, a predicate function to check for black pixels, and a Boolean flag findmin to indicate whether we're searching for the minimum or maximum boundary. The method adjusts the search range based on the predicate's result. If the predicate is true, it narrows the range by either moving the high pointer for finding the minimum or the low pointer for finding the maximum. Otherwise, it adjusts the pointers in the opposite direction. The helper methods rowHasBlack and columnHasBlack are used to check if a specific row or column contains any black pixels. These methods iterate through the respective row or column, returning true if a black pixel is found, and false otherwise. Together, these methods ensure that we efficiently locate the smallest rectangle enclosing all black pixels in the image. To solve the problem, we start by understanding the input. We have a 2D grid representing an image, where 0 indicates a white pixel and 1 indicates a black pixel. Additionally, we are given the coordinates of one black pixel, here, x, y, equals 0, 2. Our task is to find the smallest rectangle that encloses all the black pixels in the image. The first step is to determine the top boundary of this rectangle. To do this, we use a binary search on the rows, starting with the range low equals 0 and high equals 0, since the black pixel is in row 0. We check if row 0 contains any black pixels, which it does, so we confirm top equals 0. This marks the upper limit of the rectangle. Next, we find the bottom boundary using another binary search on the rows. This time, we look for the first row after the last black pixel. The initial range is low equals 1 and high equals 3, covering rows below the given black pixel. Checking row 1, we find black pixels, so we move low to 2. Row 2 does not contain any black pixels, so we adjust high to 2. This gives us bottom equals 2. With the vertical boundaries set, we now shift to finding the horizontal boundaries. For the left boundary, we perform a binary search on the columns to find the smallest column containing a black pixel. The initial range is low equals 0 and high equals 2. Checking column 1, we find black pixels, so we move high to 1. Column 0 has no black pixels, so we move low to 1, resulting in left equals 1. Finally, for the right boundary, we search for the first column after the last black pixel. The range starts at low equals 3 and high equals 4. Column 3 has no black pixels, so we adjust high to 3. We now confirm that right equals 3. With all boundaries determined, we calculate the area of the rectangle. The boundaries are top equals 0, bottom equals 2, left equals 1, and right equals 3. Using the formula for the area, bottom, top, asterisk, right, left, we get 2, 0, asterisk, 3 to 1 equals 4. This is the smallest rectangle that encloses all black pixels in the given image. In the next example, we consider a larger image where the black pixels are more isolated. Here, the input is a 5-column image with the black pixels located in rows 1 and 2, specifically in column 2. The coordinates of one known black pixel are x, y, equals 1, 2. We begin by finding the top boundary. Using binary search, we start with low equals 0 and high equals 1. Checking row 0, we find no black pixels, so we set low equals 1. Thus, top equals 1. For the bottom boundary, we use binary search with the range low equals 2 and high equals 4. Checking row 3, we find no black pixels, so we move high to 3. Row 2 contains black pixels, so we adjust low to 3. This gives us bottom equals 3. Moving to the horizontal boundaries, we start with the left boundary. The range is low equals 0 and high equals 2. Column 1 has no black pixels, so we adjust low to 2, confirming left equals 2. These steps narrow down the vertical and left boundaries of the rectangle. To find the right boundary, we perform binary search in the range low equals 3 and high equals 5. Checking column 4, we find no black pixels, so we move high to 4. This gives us right equals 3. With all boundaries identified, we calculate the area. The rectangle is defined by top equals 1, bottom equals 3, left equals 2, and right equals 3. Using the formula, the area is bottom to top, asterisk, right left, equals 3 1, asterisk, 3 to 2, equals 2. This is the smallest rectangle that encloses all black pixels in this image. Lastly, we consider an edge case where the image contains only a single black pixel at x, y equals 1, 1. In this edge case, the image is a 3 by 3 grid, and the only black pixel is located in the middle. To find the top and bottom boundaries, binary search quickly identifies both as row 1 and row 2, respectively. Similarly, for the horizontal boundaries, binary search confirms left equals 1 and right equals 2. The rectangle is defined by these boundaries: top equals 1, bottom equals 2, left equals 1, and right equals 2. Calculating the area, we get bottom to top, asterisk, right left, equals 2 1, asterisk, 2 to 1, equals 1. This verifies that even in cases with a single black pixel, the algorithm correctly identifies the smallest enclosing rectangle. The output for this example is 1. To analyze the time complexity of this solution, we start with the binary search operations used to determine the row boundaries, specifically the top and bottom limits of the smallest rectangle enclosing the black pixels. The binary search function is invoked twice for the rows, and each search operates over a range of rows with a maximum size of m, where m is the total number of rows in the image. Within each iteration of the binary search, we call the row_has_black function, which scans all columns up to n columns to check for the presence of black pixels. A single binary search has a complexity of O log m, and since each iteration of the search involves a row scan of O n, the total complexity for both row searches becomes O log m asterisk n. This accounts for the computational effort required to find the top and bottom boundaries. Next, we focus on the binary search operations for the columns, which determine the left and right boundaries of the rectangle. Similarly, the binary search function is called twice, once for the left boundary and once for the right. Here, the binary search operates over a range of columns with a maximum size of n, the number of columns in the image. During each iteration, the column_has_black function is used to check all rows up to m rows for black pixels. The complexity of a single binary search in this case is O log n, and each iteration involves a row scan of O m. Combining these, the total complexity for both column searches becomes O log n asterisk m. Finally, computing the area of the rectangle requires just a constant time operation involving subtraction and multiplication, which is O 1. When we combine all these components, the overall time complexity of the solution is O log m asterisk n plus log n asterisk m, which reflects the contributions from both row and column boundary searches. Now, let's turn our attention to the space complexity of the solution. The binary search operations themselves require only a constant amount of memory for variables like low, high, and mid. These variables remain fixed in size, regardless of the dimensions of the input image. Additionally, the row_has_black and column_has_black functions use generator expressions, which evaluate lazily and do not allocate memory proportional to the size of the input. This ensures that there is no additional memory overhead during the row and column scans. Finally, the algorithm does not rely on any auxiliary data structures and operates in place, further ensuring that the memory usage remains constant. Therefore, the space complexity of the solution is O 1, making it very efficient in terms of memory use. To better understand the efficiency of the optimized solution, let's compare it with a brute force approach. The naive method would involve iterating through every cell in the MXN grid to find the smallest rectangle enclosing all black pixels. This results in a time complexity of O m asterisk n, as each cell is visited exactly once. However, even with this exhaustive search, the space complexity remains O1 since no additional memory is required. In contrast, the optimized approach uses binary search to significantly reduce the number of cells that need to be examined. By leveraging the logarithmic reduction of the search space, the time complexity improves to O log m *n plus log n *m, which is much faster for large images. Importantly, the space complexity remains the same at O1, making the optimized approach a clear improvement over brute force in terms of time efficiency. Finally, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, if the black pixels are clustered near the starting point, the binary search quickly identifies the boundaries. However, the complexity is still dominated by the row and column checks, resulting in a time complexity of O log m *n plus log n *m. For the average case, where black pixels are scattered throughout the image, the binary search performs the same number of iterations and checks, leading to the same overall complexity. Even in the worst case, where black pixels span the entire grid, the algorithm behaves consistently, with the complexity remaining O log m *n plus log n *m. The key takeaway is that the logarithmic reduction of the search space ensures consistent performance regardless of the input. Mathematically, this is because binary search reduces the range by half in each iteration, contributing O log k for a range of size k. Each iteration involves a scan of all rows or columns, adding O, n, or O, m. When combined, the row and column searches result in the final time complexity of O log m *n plus log n *m. Here, we'll discuss some common pitfalls when solving the problem. First, failing to account for edge cases can often lead to runtime errors or incorrect outputs. For example, if the matrix contains all black pixels or no black pixels at all, these scenarios may not be handled properly unless explicitly tested. To address this, always include edge cases in your testing strategy to ensure your solution is robust. Another frequent mistake involves incorrect bounds calculation. When determining the smallest and largest row or column indices of black pixels, off-by-one errors are a common source of bugs. To avoid this, use clear, descriptive variable names like min_row or max_row and ensure you're updating these bounds carefully as you iterate. Lastly, unnecessary retraversal of the matrix is a source of inefficiency. For example, repeatedly scanning the entire matrix for each row or column analysis can significantly increase the time complexity. Instead, strive to collect critical information, such as the minimum and maximum indices, in a single pass to eliminate redundant computations. Now, let's look at 2 additional mistakes. Ignoring problem constraints can severely impact performance. For instance, assuming that the matrix dimensions are small when the constraints allow for large inputs, such as matrices with up to 1 million elements, can lead to poorly optimized solutions. To handle this, always design your approach with the worst-case scenario in mind, and consider using efficient data structures like prefix sums or binary search to optimize performance. Another issue is overcomplicating the solution. It's easy to get carried away with advanced techniques, like divide and conquer, when a straightforward row or column scan might suffice. Over-engineering can make your solution harder to implement and debug. Instead, prioritize simplicity and clarity in your approach, and only optimize further if the problem explicitly requires it. In interviews, the way you approach the problem matters as much as the solution itself. Interviewers often challenge candidates to optimize their solutions, so it's a good strategy to start with a brute force approach and then refine it. Additionally, be prepared to discuss trade-offs between space-efficient solutions, which may use in-place computation, and faster algorithms that require additional memory. For matrix-specific problems like this one, it's valuable to be familiar with techniques such as binary search in rows or columns, prefix sums for quick-range queries, and projection methods to simplify the matrix analysis. Finally, clarifying constraints upfront is critical. For instance, confirming whether the matrix contains only binary values or checking its dimensions ensures that you can account for edge cases effectively. This preparation not only helps in solving the current problem but also allows you to connect it to related ones, such as LeetCode 73, which deals with setting matrix zeros, or LeetCode 200, which focuses on counting islands in a grid. Let's explore some alternative approaches to solving the problem. One method involves row and column projections. The idea here is to iterate through the matrix row by row or column by column to identify those that contain black pixels. This approach reduces unnecessary checks but often requires 2 passes to gather all the necessary information. Another option is binary search. By applying binary search to locate the first and last rows in columns containing black pixels, you can reduce the time complexity to O, m log n, or O, n log m, depending on the dimensions, though this approach can be trickier to implement correctly. Lastly, using prefix sums can be a powerful strategy for faster queries. By pre-computing prefix sums for rows and columns, you can quickly determine if black pixels exist within a specific range. While this improves query performance, it does come at the cost of increased space complexity. Each of these methods has its strengths and trade-offs, so the best choice depends on the problem's constraints and requirements. Great job on making it to the end. To summarize, we tackled the problem of finding the smallest rectangle enclosing black pixels using efficient algorithms. Keep in mind the importance of recognizing input structure and applying the right techniques like binary search. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!